Hello. So in this example, we are doing an indefinite integral. And in this one, we are going to need a U-substitution. So I can notice that, right, this U-substitution up here has sort of a bunch of stuff under a square root. And I really only sort of know how to deal with square roots of a variable, at least at this point. So I don't really know what I would do if I'm adding or subtracting a thing, let alone having sort of like a power in there. But I do notice that if I look at this sort of whole inside bit here, this x squared plus 1, that if I take the derivative of that, I do get something very close to x. So that's sort of where I'm going to go. I'm going to make u be this thing so that when I get the du, that'll be close to the outside bit here, the x. Okay. So the first thing, I'm going to start with u being x squared plus 1. Take derivative of both sides. I'm going to get du, and this will be 2x, the plus 1, right? Derivative of that's 0. So that's just going to be dx. And I can solve for this, for the dx here. So I'm going to get du over 2x equals dx. Then I'm going to rewrite my integral, but I'm going to do it by subbing stuff out, right? So I have my integral. I'm going to leave the x out, right, because I didn't make the u for that part. I made it for what was in the square root. So then I'm going to replace what was the u for that, right? So I just have the square root of u. And then I'm going to replace what dx was here. So I'm going to get du over 2x. But I can notice, right, that the x and the x, these things cancel out. So I'm going to get, really I'm going to write this as u to the 1/2. And then I'm going to make the over 2 into just a 1/2, and then du, right? So I can pull the 1/2 out entirely. So that's just sort of a constant, so it gets sort of ignored. But for this part, right, I need to know the antiderivative of u to the 1/2. So that's going to increase the power by 1, but then I have to divide by that new value, right? So I'm going to have u to the 3/2, right, because I'm going to add 1 to 1/2. But then I have to divide by whatever the power is, in this case 3/2. And then, again, this is an antiderivative, but I want all of them, so I'm going to have plus c. And now I can clean this up. So dividing by 3/2, same as multiplying by 2/3. 1/2 times 2/3 is 1/3, right? 1/2 of 2 over 3. So that's going to be 1/3 u to the 3/2 plus c. Now, I'm not done, right? Because my answer is still in terms of u, but I wanted it, right? I gave it in terms of x, so I need to replace that, go back to x. So my u is x squared plus 1. And now I'm done. Okay. So again, I notice, right, like square root of a bunch of stuff, I don't really know how to do that on its own. But I also notice that the derivative of all that stuff, well, that's something pretty close to what's sitting outside there, right? We're pretty close to that x. So that tells me that I want to try to do the u as the thing that's inside, right? And then I sort of just went from there, and it worked out. That's usually how U-subs work, is you're like, it looks like it should be about that. Sometimes it doesn't work perfectly, and you have to go back and do sort of a little bit of a change. But usually how it doesn't work out, it's like, oh, you know, I needed to not use, you know, an x here, or I needed to include another piece here, or whatever. So usually sort of when it doesn't work, it sort of becomes clear as to why, and then it becomes easier to edit. Okay, so that's that. Hello. So in this example, we are computing an integral, specifically an indefinite integral, right? So This particular one is going to involve a technique known as the U-Substitution, or U-Sub, okay? So sort of right off the bat looking at this, I know that I'm gonna have sort of some trouble if I try to do this directly, right? Because rational functions are not something that we can really tackle very well. But there's sort of good news, there's sort of a reason to hope, as it were, looking at this, because if I look at the bottom, right, I have x cubed minus x squared plus 2. So the derivative of that, right, I'm going to have the 2 go away, and then I'm going to have an x squared in an x term, which is exactly the kind of thing I have at the top. So it's not obvious, or I should say, it's not really clear whether our U-sub will work, but it should be sort of easy-ish. Once you sort of get used to it, it's sort of plausible to see that a U-sub might work. Basically, the takeaway here is that noticing that the top is close to the derivative of the bottom, this tells me that it's worth investigating to see if I could do a U-sub. So to do that, I'm going to start by making u be the entire bottom, right? Because that's the thing that I noticed if I took the derivative of that, I get the part that I sort of saw on the top, okay? So I'm going to start by saying, okay, I'm going to let u be x cubed minus x squared plus 2. As a side note, I write my u's as a weird script thing because when I was taking calculus, people used a lot of u's and v's intermixed, and if you ever try to write a u and a v, oh man, it gets hard to tell them apart. So I developed a weird looking u so I could tell apart my own notes. So a little bit of personal history there. So I've written down my u. I'm going to take the derivative now. So the derivative of the left is just du. Derivative of the right, well, these are polynomial terms. So I'm going to get 3x squared minus 2x. That plus 2 goes away, and then I'm going to have dx, right? So in particular, that dx is multiplying everything. Now, the sort of easiest way to check to see if this works is to treat this du and dx as differentials, if you remember what we talked about differentials earlier. But the idea is that I basically want to isolate the dx and substitute out the dx up here, because I can't really do much with the integral unless all of the letters are the same, at least not at this level. That's something you might see if you took multidimensional calculus or something like that. So I'm going to solve for dx here basically by just dividing that piece over. So I'm going to have dx then equal my du divided by 3x squared minus 2x. Okay. So now I'm going to go back to my integral, my original integral. So oh man, I usually don't care, but that is a disgraceful integral sign. Let's try that again, shall we? All right, that's a little bit better. So my integral is originally 6x squared minus 4x over x cubed minus x squared plus 2 dx. So this is the original piece. Now what I want to do is I want to replace the specific thing I thought of when I thought of u, which was this bottom piece, and I want to replace my dx, and I'm going to leave everything else there. In particular, I'm going to leave the top as it is, the hope being that I'm going to use whatever's left over, the top here, to cancel out the grossness that I generated when I solved for dx over here. That's the hope. Okay, so I'm going to replace the bottom with the u that I made. So I have my u there, right? So that's from here. Then I have my 6x squared minus 4x. And then I have my dx, which is, trying to color coordinate this here, du divided by 3x squared minus 2x. Okay. Now looking at this, I can't quite just cross them out. They're not the same, right? But they're very, very close. And in fact, when I look at this, I say, okay, 6x squared minus 4x, 3x squared minus 2x, this is actually twice as big. So if I factor out a 2 there, well, I'm going to have 2 times. Now I have 3x squared minus 2x. Over u times, I still have my 3x squared minus 2x down here, and my du up there. But now, bust out yet another color. This piece and this piece are the same, so they cancel. And what I'm left with, I can now go to one color. What I'm left with is 1 over u du. And this is great news because now it's all one letter, right? I have the u and I have the du, so I can think of it as my standard sort of integral. I don't have to worry about, like, I could think of this as an x in terms of trying to think of an antiderivative. So if it were just 1 over x, right, then my antiderivative would be natural log of x. Almost, right? It's really absolute value, right? Because I don't know whether u can be positive or negative or whatever. So this thing, I can actually get the antiderivative here, which is the natural log of absolute value of u plus c, right? Because remember, this is an indefinite integral. I need all of the antiderivatives. But I don't want to stop here, right? Because what you were given was an indefinite integral in terms of x. So I should give back an answer in terms of x. That's pretty reasonable, right? Somebody was like, hey, you know, how many apples are there in a pie? And you went 27 furlong or something. They'd be like, what? Right? So like, got to give back the same thing you were given. So easy enough though, right? Because we know what u is. I just substitute the u back. So natural log of this thing, x cubed minus x squared plus 2, all in absolute value, plus c. All right, so again, I looked at this, right? I saw the bottom and I was like, that bottom, if I took the derivative, I get something close to the top, so I'm gonna try it, right? So I mean the bottom into u, calculated du, solve for dx in that form, then substitute out just the original thing I thought of as u and the dx, and then I tried to see if I could get rid of the sort of mess that came along with that du by canceling against the stuff that was still left over in the problem. And indeed that worked out with a 2 that I totally did not account for. Sorry, the 2 should have been here. This is why I look back over work. So the 2 should have been there, but a 2, right, can move in and out. So the 2 can move out, which means I just get a 2 outside, which means I just get a 2 outside. There we go. So I had to factor out a 2. They canceled. That gave me just 1 over u du with that 2 floating there. But 1 over u is just natural log of absolute value of u, again with the 2, plus c, because it's an indefinite integral, so I want all the antiderivatives. And then substitute the u back in to get my thing in terms of x, and there's my answer. Okay, so that's that. Hello. So in this example, we are doing an indefinite integral, but here we need that technique of a U-substitution or U-sub. And I sort of can see that I'm going to want to U-sub because looking at this, right, I have e to some really gross power up here, and really we don't know how to deal with that as a general rule. So really I'm really hoping that I can make this into some sort of e to the u form, because that's really the only thing I know an antiderivative of at this point in the class. So I'm going to start by just sort of trying that and seeing what happens, right? So I'm going to take my u, and I'm going to make my u be the power of e. So it's going to be x squared plus x. And then taking the derivative, so I'm going to get du, which is 2x plus 1 dx. And solve for dx, So that's going to get me dx is du over 2x plus 1. Okay. So now I'm going to substitute out the thing that I sort of initially noticed for the u and the dx, and then see what I have to do from there. So my original integral was 4x plus 2 e to the x squared plus x dx, which when I substitute everything out, I'm still going to have the 4x plus 2, and I'm going to have the e, but now I have e to the u, and when I sub out the dx, I'm going to get du over 2x plus 1. And now the hope is that I can sort of use the two things of x's to cancel each other out in some way. And again, they're not, right, these aren't quite the same, but they're close, right? I can pull out a 2 here, and that should make them basically the same. That's the hope. So I'm going to try that. So pulling out a 2, I get 2x I get 2 times 2x plus 1 e to the u du over 2x plus 1. And indeed, now I have 2x plus 1 in the bottom and the top, so those cancel. And that's going to get me now, I can take the 2 out because it's a constant against the whole thing. So I'm going to get 2 times the integral e to the u. Right, so the 2 came out, that went away, e to the u du. And this is nice, right? Because the integral of e to the u is e to the u. It's the same thing, right? Because I have everything in terms of u, there's no x's left over. So the 2 is still there, but when I take the integral of e to the u du, I just get e to the u plus c, right? Because I want all the antiderivatives, not just one. But then I have to give it back in terms of x, right? So I have to sub out what the u is. So I get 2, excuse me, 2 times e to the x squared plus x plus c. Okay. So again, I sort of looked at my original problem, right? Looked at my original problem and I thought, I don't really know what to do with that power. But looking at it, right, I see like 2x plus a constant. So I have a sort of linear term, a linear polynomial, right? mx plus b. And that's what I have out front. So the derivative of this is something like that. So I hope a u sub will work. So I make the u be the whole power, take the derivative, solve for dx, then sub out the power with u, sub out the dx with the du and the x stuff, and then sort of manipulate so that I can cancel the rest of the x stuff. If I can't do that, then it's not a good u sub, or it's at least not a full u sub. So fortunately, that worked. Those canceled. I can pull the 2 out because it's a constant, and that gets me e to the u. The integral of e to the u is e to the u plus c, right? Because it's a still a indefinite integral, right? I want all the antiderivatives. And then replace u with what I originally made it, x squared plus x. Okay, so that is that.